Okay, students, so last time we talked about the elastic rebound theory. Now we're going to be talking and how faults are formed and the stresses and the strains related to that. So now let's talk about the energy that actually is stored in those faults. As more and more energy goes into the rocks, once it breaks, it emits that energy outwards, right? Just like what we had up here in our focus here, it goes radially out from that central point and then to the surface, right? So now we're going to be talking about a little bit what the seismic waves are, what happens when they get emitted. So a seismic wave is just any energy that is actually caused by the sudden breaking of those rocks, or that release of that buildup of stress and strain over time. There's two different types of seismic waves. We have what we call body waves and surface waves. Body waves are two types of body waves. We call them either primary or secondary. Sometimes we call those primary waves compression waves or P waves, and the secondary waves are S waves or transverse waves. So a compression wave is just what that sounds like. And let's step back for a second. The difference between a body wave and a surface wave. Body waves means that it goes through the whole subsurface. So you can get, for example, if we had an earthquake here in Pembroke, those seismic waves would go all through the subsurface of the entire Earth, and you'd be able to actually pick it up on the other side of China, right, as it goes through the whole center of the Earth. Now, certain waves can go through solid materials and some can't. So P waves, for example, can go through solid materials and the magma core of our inner core, the molten iron core. And whereas surface waves are only stay at the surface. They come towards the surface and then they go out from there and they dissipate quickly thereafter. So they don't go a long distance. But the surface waves are really what's causing most of the movement on the surface and causes most of the damage that you have at an earthquake. So P waves are what we call compression waves. So I got a slinky here, and hopefully we can see this. So the slinky here, and a compression wave means that it gets pushed together or pulled apart. Okay, so I'm going to actually get this and watch it go back and forth. You can kind of see a wave here. I know this is not very good. Maybe hopefully get this way. I have it here, and then release some of the energy, and it goes back and forth in between the wave, the thing. So it basically is compresses and pulls apart as the wave goes through the system. Okay, that's a P wave. We sometimes call it the primary wave because that's the wave that wave is fast, goes through solid materials faster than secondary waves. So if you had an earthquake here in Pembroke and we had a seismometer in Lumberton, the P waves are the first ones to arrive. So that's why we call them primary waves. Whereas the S waves would be the second ones to arrive, which means that's why we call them secondary waves. Okay, so also P wave, it goes for P for pressure, and S wave is for a transverse wave or a shear wave, where they move back and forth like this instead of back and forth this way. They're moving this way. Okay, and so those are two types of body waves. Now surface waves, like I said, are on the surface, and I'll show you some of the examples of these. A love wave and a Rayleigh wave is two different types of them. Okay. So this is your compression wave. Now notice as it goes through, it compresses the material and then stretches it out. Okay, let's watch it again. Watch this black box right here as it goes through again. It gets compressed, pulled apart. Okay, so it goes together and then apart, together and apart, and it just moves through the whole system. Okay, so it's the fastest kind of seismic wave. It can go through solid rock. It goes through fluids. Basically, your sound waves are very similar to compression waves. That's really what they are. Is just sound waves as they go through the air, but are the compressive forces or compressed waves as they go through it. Okay, so these are, like I said, are the fastest waves. So the ones that are going to reach here first. Now the shear wave means that it's going back and forth like this. Okay, notice that it's kind of like this. What happens to the black box again as it goes through? It gets sheared upwards and sheared backwards on the side. Now it can go up this way, it can go this way. It doesn't really matter, but it's the shear motion of the particle to particle. So, for example, if I have two atoms right next to each, two rocks in the atoms, you have two atoms in the rock. I mean, so the pressure is going to push on this one, the pressure is on the other one. Okay, And whereas a shear wave means that this one right here is going to be sheared back and forth through it. So the shearing motion actually slows it down. It actually absorbs some of the energy as it goes through the system, whereas it's much more efficient for a P wave to actually transfer through the system. So the S waves are a little slower going through a rock or materials. And S waves don't go through fluids. Once they go to a fluid, the energy is dissipated so much, or gets absorbed so much, that it actually dies out. And so it doesn't go through a fluid. This is part of the reason why we know that the subsurface has the different layers to it. We have the mantle, the core, the inner core, and all that, because as these seismic waves go through, as they hit different materials, for example, the P waves can go through the liquid, whereas the S waves cannot, and we can then see how they reflect and refract off those different layers. Okay. So now your love wave is a little bit different. It's going back and forth, but notice there's more motion on the top here than there is on the bottom. So it's this side-to-side motion, but it's different. Whereas the S wave, it goes side to side, but it's the same as it goes all the way through. It's less rigid on the top, so it can move more. Whereas the bottom, it's more rigid, so it just stays put. So imagine having a post in here or a foundation in this, and how it's going to actually be ripped apart as it goes through that system. Now Rayleigh wave, same way. Notice it's more motion at the top, less motion at the bottom, and these ones are some of the slowest ones out there. They're kind of like the waves of an ocean. Okay, so we measure these waves through what we call a seismometer. And these seismometers are just these devices that record shaking of the Earth's surface. So really what's happening here is, in the old-fashioned ones, what they would have is they would have this pin on a spring, and the piece of paper would be right here, right? So as the pin goes up and down, it's going to make these marks on the paper. Sorry. And it's really not the pin that's moving up and down, it's the land that's moving up and down. It can move up and down or side to side or whatever. It's actually marking that, whereas the pen itself stays pretty still. And so this is what we call a seismometer. Okay? Now today this is done digitally. It doesn't have that actual pin, but that's okay. It still works the same kind of concept, where it's actually measuring the strength or the vibrations within the ground itself. So a seismometer is the device to do it. The seismograph, okay, is the recording device for the permanent record, and the seismogram is that actual paper or a digital record of just one thing. I don't really care that you understand all the differences between these. Just know that we can record them on the surface. Now remember, these waves all travel at different speeds through the system. So you have an earthquake, and then you have the P waves, the S waves, and then the surface waves come through. So if you are, say an earthquake here happens here, and we have 3 different stations, let's say Pembroke, Lumberton, and maybe this is Wilmington, what we'll find is that the earthquake goes off, and then as the P wave goes out, it arrives first at this place, but it has to go further, so it actually arrives second there, and then here. You might see it down here in these different records. So here's the P wave that arrived first, then this one, and then this one. Now the S wave might take longer to get there, so it comes behind slower. So here's the S wave arrival, and another S wave. This is kind of like, sorry, I'm really stuffed up today, so I might be sounding a little clogged, but I have allergies really bad today. So this is kind of like if let's say we had 3 different people, and these 3 different people left, or 2 different people left Pembroke here and went to drive somewhere. Let's say we're going to drive to Lumberton, and then after Lumberton we're going to go to Wilmington. Well, if let's say I'm driving and I have a Volkswagen Bug, a really slow Volkswagen Bug that doesn't go very fast, right? And where another student has maybe a Ferrari where they're just killing it down the road, right? Well, we leave at the same time, but we won't get to this location at the same time because one's going faster than the other, right? And so the student in the Ferrari is going to get to Lumberton first, and then get to Wilmington first, right? And then I have what we call the lag time, or the time that I hit Lumberton or to Wilmington might be at these different times. And so what we record here, let's say if my rate is the same the whole way through and the other student's rate is the same as the whole way through, we can actually understand the distance that's required as we go if we go at a constant rate. So how we use this is that we know the constant rate in which a P wave goes through the Earth. We know the constant rate in which the S wave goes through the Earth for the most part. And so we can actually detect where earthquakes are in the world by their arrival times of a P wave, the arrival times of the S wave, and then what we call the lag time in between, or what we call the SP time, okay, which is the difference between the two. Okay, so how we do this is this, and you'll do a similar activity like this in your homework this week. And so what you'll have here is you'll have your P wave arrivals here, your S wave arrivals here. Okay, let's say we have an earthquake, and that first earthquake is recorded in first Denver here. And at Denver, we have a 3-minute interval between your P wave and your S wave. Well, that 3-minute time interval actually correlates to an earthquake that is about 2,000 kilometers away. Well, therefore we know that earthquake is somewhere along this line. Somewhere along this line. But we don't know where along this line. We just know it's somewhere along here. So it could be up in Canada, in the middle of the United States, over here in the near Oregon, Seattle area, maybe down in California, anywhere along that line. We don't know where. Okay, it's really a sphere, but on our surface, this is where the epicenter would be, right? So, well, if we get another earthquake, let's say we get another seismograph or seismogram, and this one is from St. John, New York. Well, in St. John, New York, there's an 8-minute interval between the P wave and the S wave arrival. Okay, well, that 8-minute interval might actually correspond to about 5,200 or so. Okay, so we know that now that earthquake is somewhere along this line as well, but it has to be along this one, both of them, so it's where they intersect. So we know that the earthquake is either up here near Seattle or down here near Carlsbad, California, right? So it has to be in one of those two places, but we still don't know which one yet. So we have to go to the third place. And so we go to Lima, Peru, and we have a seismogram that has a 12-minute interval now, and that one corresponds to about 9,000 kilometers. And so with that, we can go back and we can pinpoint where the earthquake was. And if we get more and more of these, we can pinpoint it to a smaller location until we know exactly where the earthquake was. So this is how we use. We use what we call triangulation to figure out where earthquakes were in the past, because we don't have seismometers everywhere in the world. We only have them in certain places, and so we use that to be able to figure out where those earthquakes are. Okay. Now, how do we classify earthquakes? Well, we classify them based off of three basic scales. Two of them just build off each other. The Richter scale and the moment of magnitude scale actually build off each other. The Richter scale is an old scale that we don't use very much anymore. The public still uses it. The media uses it because most students or most individuals understand the Richter scale more than they do the moment of magnitude, but they're based off of the same thing. Okay, so the Richter scale is based off what we call ground motion. How much motion actually is on the ground itself, is moving. Whereas the moment of magnitude scale actually improves on that. It still uses ground motion to be able to understand how big the earthquake is, but we also look at how much fault displacement there was and how much energy there is. So moment of magnitude really looks at the amount of energy that actually is released, whereas the Richter scale looks at just about how much ground motion is exhibited. Well, there's some relationships here, and these are important relationships. One here is that we have, let's see here, in energy difference, each time we have from a magnitude maybe 1 earthquake to a magnitude 2 earthquake, we have 32 times increase to that earthquake. Right? So from a magnitude 1 to a magnitude 2, it's 30 times more energy is released. Okay? Well, if I go to a magnitude 1 to a magnitude 3, it's not 32 plus 32, okay? It's 32 times 32, okay? That it goes to. And so it's the difference over here. Whereas in ground motion, it's not a 32 log scale, it's a 10 log scale. So it goes from 10 times, so from 1 to a 2 is a 10 times difference. From 1 to a 3 is a 100 times difference, 10 times 10. Okay, we'll come back to this in just a bit.